In this set of notes, we're going to continue looking at hypothesis test. So previously we talked about the basic setup of a hypothesis test, and in that setup we talked about evaluating the evidence in the statistic via the p-value. And we saw that instead of the traditional way that we think of hypothesis tests being calculated, we could also use permutation test or randomization test to also perform hypothesis test. So in this set of notes, we're going to go back and look at the more traditional methods, and we're going to look at where some of those formulas come from, similar to what we did with confidence intervals. Now, one thing we are going to do slightly different in portions of the notes is instead of working with the p-value, we're going to work with the rejection region. And so you may or may not have seen rejection regions before. Some intro stat courses will teach the rejection region. Majority just teach the p-value method. So this is a good alternative method to know about. You end up with the exact same conclusion as you would with the p-value. It's just a different way of looking at it. So here in the first part of the notes, this section is actually from Module 12.2, and I've just placed this here for your convenience. And again, this is that just kind of overview of hypothesis test. And you'll notice here we've got the steps of a hypothesis test. And again, in this step 4, this is where I was talking about, we had talked about evaluating that evidence by using the p-value. And so again, in this set of notes, we're going to look at something slightly different, which is looking at what is known as the rejection region. So take a moment, pause the video, make sure you review, those 2 pages of notes, and when you come back, we're going to talk about rejection regions. All right, so previously in the notes, we had this example. It's the example that is on page 1, and so we use the test statistic y bar to make our decision. And what really we're doing is we want to find a value c, so some constant, such that we conclude that HA or the alternative hypothesis is true if y bar is greater than or equal to c. So this region is what we call our rejection region. So if we think of in terms of what our sampling distribution looks like under the null hypothesis, if that sampling distribution is normal, we would essentially be looking at something like this, where at the center of the sampling distribution, we have the value under the null hypothesis. So in other words, what I mean by this is the value of the parameter under the null hypothesis. And what we were doing as we were looking, and if this were a right tail test, we were looking at where our observed statistic fell in this sampling distribution. And essentially, if y bar was close to the value under the null, we said we probably don't have that much evidence because we expect the statistic to vary some. Whereas if the statistic appeared far away from the value of the parameter under the null hypothesis, that might suggest some kind of evidence in favor of the alternative. So what we're saying is C is going to be that value or that end point in the sampling distribution, assuming that the null hypothesis is true, for which once that observed statistic is further away or past C, that's when we're going to be able to reject the null. And again, I'm writing this in terms of our right tail test. Of course, if we had a left tail test, we would be looking down in this region, or a two-tail test, we would be looking in either direction. So we can consider the following rejection region, and it says we're going to reject the null hypothesis if y bar is greater than 5 foot 11 inches. So again, we're still looking at that example from page 1. And so the idea is if we take random samples of 10 males and we observe that y bar is equal to 6 foot 2 inches, then we would reject the null. And again, that's because y bar has fallen into that rejection region, whereas if y bar were equal to 5 foot 10 inches, we would not reject the null. So really what a rejection region does for us is it gives us our evidence in terms of the endpoints on the sampling distribution, whereas the p-value, what it is doing, oops, let me bring this back to a reasonable size here, it is evaluating the evidence in terms of the area under the curve. And so that's why I was saying earlier, it doesn't really matter if you use the rejection region or the p-value, you're really looking at the same information. And so here's our formal definition here. we have that the rejection region is the interval originating from the sampling distribution of the estimator, assuming that the null hypothesis is true, that leads to rejection of the null hypothesis in a hypothesis test. The other thing that we need to talk about in hypothesis testing are errors in hypothesis testing. We're going to focus on that for just a moment in these notes. So there are two types of errors. There are what we call a type 1 and a type 2 error. Type 1 is when we reject the null, but the null was really true. And a type 2 is when we reject the null and the alternative is really true. So one thing to keep in mind here is any time that we conclude a hypothesis test. So for example, let's say the conclusion of our hypothesis test is we reject the null hypothesis. There is always the possibility that we have committed a type 1 error. Okay, so that's one reason that we define that significance level. It helps us define what our allowable amount of type 1 error is. On the other hand, if we fail to reject the null, there's always the possibility that there is a type 2 error. And in the definition here, I do want to kind of note this. So I've included it this way because different texts will put this different ways. Really, when we don't have enough evidence, our conclusion is to fail to reject the null. We never actually accept the null hypothesis, but I often see when type 2 error is defined, it will say we accept the null. So I just want you to be aware of that. You know, keep in the back of your mind, we never actually accept the null because we don't evaluate any evidence in favor of it. We're not evaluating the null. We start out by assuming it's true. But I do see that language, you know, out there in the world. So I just want you to be aware of that. When you see that, it's not technically true, but it is commonly used when defining these error terms. So really when you see accept the null, what that really means is we have failed to reject it. And then typically we use alpha to denote the probability of a type 1 error, and we use beta to denote the probability of a type 2 error. So what we're going to do next is let's look at that example again and actually see how we could calculate alpha and how we could calculate beta for a given scenario and see what these errors actually look like. So again, we're going to test if the average height of an American male CEO is larger than 5 foot 9 inches. And here we're going to use that rejection region of y bar greater than 5 foot 11 inches. So assume we have a random sample of 10 American male CEOs from a normal population with a variance of 9. So notice we are saying that our population variance is equal to 9 here. So the first thing we're going to do is we're going to calculate alpha. And remember that alpha is really your type 1 error. And so by definition of a type 1 error, this is going to be the probability that we reject HO given that the null is true. So all we're doing here is writing out, what this definition of a type 1 error is. And so now what we can do is we can write this in terms of our particular problem statement. Since we're using rejection regions, we know that we reject the null when y bar is greater than 5 foot 11 inches. So this is the probability y bar is greater than or equal to 5 foot 11 inches, given the null is true. Well, our null or our hypotheses in general are always about the value of the parameter of interest. And so since we're interested in the population mean here, if you'll recall, since we're testing to see if the average height of the American male CEO is greater than 5 foot 9 inches, under the null hypothesis, we assume that mu is equal to 5 foot 9 inches. So here, if we're given that the null is true, this is the same thing as being given that mu is equal to 5 foot 9 inches. So let's go ahead just to make the math easier here. Let's convert these over to just inches. So notice this is going to be equal to the probability that y bar is greater than or equal to 71 inches, given that mu is equal to 69 inches. All right, now we've got some other information here, and what we know is some distributional information. So since y1 through y10 are IID normal, in other words, they're all coming from this normal population, And again, we're assuming under the null hypothesis that the mean is 69 inches, and we know that the variance is equal to 9 inches. We know something about the distribution of y bar under the null hypothesis. So under the null hypothesis, we know that y bar is also going to be distributed normal with mean 69 inches, and then the variance is going to be equal to sigma squared divided by n, or 9 divided by 10. So we can use this information to help us find the probability that we're interested in. So notice here that alpha, which is again equal to the probability that y bar is greater than or equal to 71, given that mu is equal to 69, well, what we can now do is we could convert this over to a standard normal to find those probabilities. So what we're going to do is convert this by taking y bar minus 69 divided by the square root of 9 divided by 10. So in other words, I'm standardizing y bar, and anything I do on one side of the inequality, I have to do on the other one. And then the other thing I'm going to do is I'm going to drop that condition. And the reason for that is I've conditioned on mu being equal to 69, but notice that I have now incorporated that into the probability. And how we've done that is notice that in the standardization, we are standardizing by that value of the parameter under the null hypothesis. Now, one thing I will stop and say here is this step isn't actually necessary. So typically when these are taught, we do the conversion over to the standard normal, and the reason for that is back in the day we would use standard normal tables to find these probabilities. It is possible now with software such as R to just work directly with the distribution that we have in this step right here. Change my pen over. And so in other words, what we could do is we could work with a normal that has mean 69 and that variance of 9 divided by 10. So that is completely possible. So this last step that we're doing here, this conversion to the standard normal, we don't actually have to do this step. But since we have done that conversion, notice that this suggests that z, which is a standard normal, is greater than or equal to 2.1082. So we could easily find this probability either by working with R or by working with a standard normal table. And we would find that this is equal to 0.0174. So notice in this particular case, if we use this rejection region, that the probability of that type 1 error, or alpha, is fairly small. We could also calculate betas, so let's see how we do that, and it's going to be very similar. So first thing we're going to do is let's just write out what beta is equal to. Beta is equal to the probability of a type 2 error. And again, by definition, this is the probability that we fail to reject the null. But again, I think often just to make it easier to write, we're going to write except the null. Again, keeping in mind that really means that we have failed to reject it, given that HO is true. Okay. And again, we can write this in terms of our problem statement. So we accept the null when y bar is less than 5 foot 11 inches. Now 5 foot 11 inches is the same as 71 inches. So to make this easier, I'm just going to go ahead and write it in terms of inches, given that the alternative is true. Now in this case, notice we're saying the correct value of mu is 5 foot 10 inches. So notice in order to calculate beta, we actually do have to specify a specific place in the alternative hypothesis. We did not have to do this when we were calculating alpha. So here, since we're going to assume that under the alternative, that specific place of 5 foot 10 inches, this is the same thing as mu is equal to 70 inches. Right? So now we're making the assumption that mu is equal to 70. So now the distribution of y bar is still normal, but now the mean is going to be at 70 inches, and we still have variance 9 divided by 10. So we can do the exact same thing that we did before. We're going to standardize y bar so we can use the standard normal. But again, keep in mind you could have worked directly with this normal distribution since we have software that can do that for us. But here I'm going to go ahead and do the standardization. So this tells me that beta is equal to the probability that z is less than 1.0541. And again, this is going to be equal to, if we use software, 0.8531. So notice that beta in this particular case is fairly large. So this means that if the true mu in the alternative is equal to 5 foot 10 inches, we're probably going to make a type 2 error and conclude that the mu equal to 5 foot 9 inches is true. And the reason for this is the place that we have selected in the alternative hypothesis to evaluate beta at is very close to the value under the null hypothesis. So what would happen to beta if we choose a true value that's actually further out in the alternative hypothesis? So in other words, what if we look at that correct value is mu is equal to 6 foot? So you would do the exact same process, and what you would come up with, and I'll leave you to confirm that you get the same thing, but using the standardization technique, we would end up with the following. And we end up with a much better probability. So if the true value of the parameter is further out in the alternative compared to the null, you end up, your value of beta shrinks. Okay, we're going to look at a picture of why that is true. Right? So kind of just in summary of what we just saw here, if we want to test the following hypotheses with this rejection region, no matter what, alpha is equal to 0.0174. But the value of beta, or the probability of that type 2 error, is going to depend where in the alternative the actual value of mu is. And notice the further we go out in the alternative, we do decrease what our type 2 error is. So again, let's look at a picture of what this looks like. And so to start out with, what I'm going to do is I'm just going to draw my number line down here at the bottom. I'm going to do this in inches. And so let's look at where some of these values that we've looked at are. So the first one that I'm going to mark here, this is going to be my value under the null hypothesis. So this is my null value. Right? I'm going to go up a little bit. I've got 70. A bit further is 71. And a little bit further is 72. All right. So first thing we're going to do is let's look at what the distribution looks like when mu is equal to 72. So if mu is equal to 72, let me change my pen color here. So notice this is what we had when mu was 6 foot. So let's draw what this normal distribution is going to look like. So again, we're looking at the distribution of y bar, and this is a little bit of a rough sketch here, but remember that the variance of y bar was equal to 9 divided by 10. So therefore, if we want to look at the standard deviation of y bar, that's going to be equal to the square root of that, which is about equal to 0.95. Remember that by the empirical rule, we expect 99.7% of observations to be within 3 standard deviations. So if I go down 3 standard deviations, for this normal distribution, I'm here, up here. So, this normal distribution, even though it's rough, is fairly close to what it should look like. All right, so the other thing that we need to mark here is let's mark our rejection region. So remember, our rejection region is at 5'11". So our rejection region is here. Okay. So now let's look at some different pieces for this distribution. So when the true value of mu is equal to 72 inches or 6 foot, notice that anything that falls to the left of the rejection region, or in other words, this whole piece right here, this is going to represent our type 2 error. And so this area under the curve, this is where we're getting that 0.1469. Okay. Now let's look at the other possible distribution, which was when mu was equal to 5'10" or 70 inches. So in other words, we were here. So at the peak of this distribution, the second one is going to fall here. And I'm kind of running out of colors, but get the idea. So this normal distribution would look like the following. So we can see up to the rejection region, and here I'll just kind of do this one dotted because it's kind of falling behind the other one. Notice that when we're closer to the null hypothesis, in other words, we're in the distribution where the true mean is equal to 70 inches, our type 2 error is now all of this area for this distribution. And of course, this is extending down to the x-axis. So we can see we're getting much more area of this curve where we're going to have a type 2 error. And so this is where we have the 0.8531. So again, the big idea or the take home here is that if we know where the null value is, when we specify a particular spot in the alternative hypothesis, which again, that's going to be anywhere to the right of this value, really what we're doing is we're shifting over that entire sampling distribution to the right. And the further we shift that sampling distribution of y bar to the right, the further we go this way, the less of that distribution that is going to fall to the right of the rejection region, which is this piece right here. So in other words, the less of that distribution that is to the left of the rejection region, the smaller our type 2 error is going to be. So if we went all the way out here, we drew another normal distribution, notice there our type 2 error would be essentially 0. So here's another example, just again to illustrate that point, and I'll let you look at this on your own. This one says, suppose we change our rejection region. So here, we're not changing the true value of mu, we're actually changing what we're considering to be our rejection region. And you can see as you change your rejection region, this time you are going to change alpha, and of course we're going to change beta. But what you're going to see in this example is we get much more reasonable values for beta, because we've taken our rejection region and we've pushed it further. We've pushed it closer to the null hypothesis, not further into the alternative. So take a moment and look over this example and see how those values change. And then here in this table, we have kind of the comparison between the two. Notice we have two different rejection regions, and then we also have two potential values for the type 2 error depending on where in the alternative we specify the true value of mu, and then we have alpha. And we can see that by bringing our rejection region closer to the value of the null, we get gains in beta, and then we also get better values. We get a slightly worse value for alpha, but much better values for beta. So again, take a moment and look at this. And what this does is this suggests for a fixed sample size, when alpha increases, beta is going to decrease. When alpha decreases, beta increases. So to reduce both alpha and beta, you're going to have to increase the sample size. All right, so we're going to look at some common large sample hypothesis tests. my suspicion is that this section is probably going to be completely review. You have seen these before. So again, these are really just a reminder of these large sample hypothesis and seeing how these relate back to the idea of the sampling distributions that we have talked about before when we have large samples. So if you'll recall in Module 8, we had a table that listed some parameters of interest, and we want to conduct a hypothesis test for these different parameters. And so common parameters that we have here are the population mean, a population proportion, difference in means from independent samples, and a difference in proportions from independent samples. And what we saw previously was, as a result of the central limit theorem, if the sample sizes are large enough, all of the point estimators theta hat are approximately normally distributed. For any of the target parameters in the table, we can then test these hypotheses. And so notice here in these hypotheses, we have specified a null theta naught. Theta naught is just the hypothesized value of theta. So in our previous example, we had our hypotheses were under the null. We had that mu was equal to, let me just double check that, 5'9", which again, that was 69 inches. So here, your theta is the mu and your theta naught is the 69 inches. Now this particular test we're looking at here is an upper tail test, and the reason for that is we have theta greater than theta naught, but of course we could look at left tail or two tail tests, and we'll have a summary of those here in just a moment. But the main idea is we want to reject null if theta hat is large. So using standardization, we know that theta hat minus the value under the null divided by the variance of theta hat. If we standardize that, that's going to follow a standard normal distribution. So in order to find C, what we can do is we can actually use that type 1 error. And what we can do is we can solve for the C. And solving for C will give us our rejection region. So this is how hypothesis tests are traditionally set up, so that the standard normal table could be used. Again, alternatively, you could work directly with the sampling distribution under the null and the observed value of the estimate. So the standardization here isn't actually necessary, because if we work directly with the sampling distribution of whatever our estimator is, we have software that can calculate all those distributions. And so here is the summary for the different types of tests. So, oh, that's a mistake. I'll fix that in the notes. That should say under H naught, we've got theta equal to theta naught. But here you've got your right tail, your left tail, and there's also an error there. So yeah, I will fix this in your notes. That should say a not equal to there. So you have your right tail, left tail, and two tail test. Either way, we're going to use the same statistics. And here's how you set up your rejection region. All right, so let's look at an example of this, of how we're going to find our rejection region. And again, this is going to be pretty much review, because how you find the rejection region actually ends up being very similar to how you find a p-value, because it's just working with the endpoints instead of working with the value, or probably the area under the curve. So a sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.70. He interviews 100 families, obtaining a mean of 4.8 with a standard deviation of 8.0. And so we're going to test his claim using alpha equal to 0.1. So the first thing we do need to do, let's talk a little bit about our assumptions. Here we've got that he interviews 100 families. We do need to make the assumption that that is a random selection of families, because we don't want to introduce bias. And then a further notice, since we have 100 families, n's greater than 30, so we know our central limit theorem here is going to apply. So in terms of our hypotheses, we have the following. Under the null, we have that mu is equal to 4.7, and we're going to try to prove that mu is greater than 4.7. Right. So the first thing I'm going to do is just set up my test statistic. So here z is going to be equal to y bar minus the value of the population mean under the null hypothesis divided by the standard deviation of the statistic. So here we've got sigma divided by the square root of n. Now, one thing that I do want to make sure to point out is in the denominator here, notice we do have the standard deviation of the statistic. If this standard deviation depends on the value of the parameter in the null hypothesis, make sure that you're using the value of the parameter under the null. So here we have a parameter, it's sigma, but it's not the parameter that's in our hypothesis, so we're fine. But for example, when you work with proportions, the standard deviation of a proportion does depend on the value of the proportion. So you want to be careful there, and we'll see that in the next example. Now here we don't have sigma, but we do have our sample standard deviation, so we're just going to go ahead and estimate that using the sample standard deviation, using that plug-in principle that we've talked about before. And now we're going to take our values from the problem statement. All right, so now let's talk about how we're going to find our rejection region. So to find our rejection region, we've converted our test statistic over to z, so we know that we're working with a standard normal distribution. So let's draw our standard normal. And we know that we're going to use alpha equal to 0.1. So in order to find our rejection region, what we're actually going to do is in our normal distribution, we've got a one-tailed test. We're going to put area 0.1 here. And then our rejection region is going to be defined by what this endpoint is right here. We can use software to help us find this endpoint, and it ends up that this endpoint is equal to 1.282. So that's going to define our rejection region. And so for our rejection region, what we're saying is if z is greater than or equal to 1.282, then we should reject the null. So in this case, we are going to reject, and then we would conclude our hypothesis similar to how we would conclude what we saw in the previous note sets. We could say, you know, at the 10% significance level, we have enough evidence to reject the claim that the average number, we have enough evidence to reject the claim that the average number of people per family unit in the large subdivision is equal to 4.7, and we can conclude that it is greater than 4.7. And so again, using the rejection region is very similar to using the p-value. It's just we're working with the endpoints on the distribution instead of the area under the curve. So here's another example. So this one we are going to work with a difference in proportions, but it's going to be very similar. So Time Magazine reported the results of a telephone poll of 800 adult Americans. The question posed to the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for health care reform? And the results of the survey were as follows. So notice again, we're going to work with a difference in proportions. Is there sufficient evidence at the 0.05 level to conclude that the two populations, smokers and non-smokers, differ with respect to their opinions? And so, you know, the first thing we want to make sure that we can do is, have we met sample size requirements? So here, if we look at the counts from our two different groups, we can see that these are fairly high. So the central limit theorem is going to apply here. So the next thing we're going to do is set up our hypotheses. So under the null, what we're saying is that the proportion of non-smokers is equal to the proportion of smokers, and under the alternative, we're saying that they are different. Now, alternatively, notice we could also write our hypotheses as follows. I almost like this way better, and the reason for it is it makes it very clear that this difference in the proportions, that is our parameter. So that entire piece that's highlighted is the parameter. I feel like when we write it the way on the left, you know, that's not always as clear to people that that whole difference actually is our parameter. Now, of course, the other assumption I didn't mention up above is we do have to assume that these were a random sample of people. That's one of those things that often gets, I think, kind of overlooked, especially in introductory examples when we talk about hypothesis testing or confidence intervals. But you always want to keep that in mind, especially in practice, is, you know, you really do want those random samples, and the reason for that is that's going to help you control for bias. Now, of course, you know, there are other ways to help control for that. You know, you might have to end up weighting your sample or doing some other things, but you really want to keep that in mind. So the next thing we're going to need to do is calculate our test statistic. So for our test statistic, our observed statistic that we're interested in is going to be p hat non minus p hat s. And then, this is again the reason I like writing my hypotheses the way on the left, is it makes it very clear that under the null hypothesis, the value of the corresponding parameter is 0. So really we have a minus 0 here in the numerator, and then in the denominator, we're going to have the standard deviation of our statistic, p hat for the non-smokers minus p hat for the smokers. That's the standard deviation of that statistic. And so let's go back up to our chart that we have and notice that is going to be our standard deviation that we want. Notice that the standard deviation does depend on P1, P2. In other words, it depends on the parameters. We don't have the values for those parameters, and we don't know the value of these. You know, under the null, we know the value of their difference is 0, but that doesn't tell us what their actual values are. So again, we're going to use the plug-in principle and use the plug-in principle to plug in what the corresponding statistics are. And I'm going to have you, plug in those values on your own and double check, but you should get that our statistic is equal to 8.986. But one thing that I want you to notice here is in the first example we worked with a single mean, in this one we're working with a difference in proportion. The overall idea of what you're doing here is the same. You're taking your estimate, or your estimator, you're subtracting off the mean of that estimator, assuming that the null hypothesis is true, and then divided by the standard deviation of that estimator. Now, of course, we've had to make, a couple changes here. We've had to use that plug-in principle because we didn't know the value of the parameters, so we're going to plug in the value of the statistic. All of these key ideas, they don't just work for these particular estimators that we look at. You can extend these ideas to other estimators. Now, I don't want to say there's this blanket extension, but you can use that as a starting point and see, okay, will these same ideas work? Do I need to make slight modifications? And so that's why it's really good to kind of dig in and really have a good understanding of how these formulas are set up, because it can help you later on see the relationship of how to maybe set up new formulas. Now again, same idea as before. We're going to go through to find our rejection region. What we would do is we would draw our standard normal distribution. Now here we've got alpha is equal to 0.05, and we're looking at a two-tailed test. So we're going to have to find the endpoint that is both to the left and to the right of 0. And then in terms of the area, we're actually going to split the area between the two tails. So since we're looking at alpha equals to 0.05, what we're going to have is 0.025 here, 0.025 here, And so notice this is the endpoint that we want. And so that endpoint is that all familiar endpoint that you've probably seen, a million times, 1.96. So here, what we're doing is for our rejection region is going to be if the absolute value of z is greater than or equal to 1.96. And obviously, z is far greater than 1.96. So in this particular case, we are going to be able to reject the null. And so in terms of our conclusion, what we're saying is at the 5% significance level, we have enough evidence to conclude the proportion of smokers who agree with the tax differs from the proportion of non-smokers who agree with the tax. So in terms of the conclusion, notice how I'm wording the conclusion is no different than if we had used a p-value. So again, whether you use the rejection region or the p-value, you end up with the same conclusion, but being able to work very fluidly and having a deep understanding of what's happening in these sampling distributions, that's what your real aim here is, especially for this course. Not so much just can you get through these calculations, but can you see where these are coming from and how they're related to the sampling distribution. So that's going to conclude this note set. And the next one, we're going to talk about some more concepts with hypothesis testing.